Hi, welcome. Today we're going to talk about non-abstract large system design. Some people call this NALSD.
Hello, my name is Julia, and I'm working for the BigQuery team as a site reliability engineer out of the Google's Zurich office.
And I am JC. I also work from the Zurich office, but then as a site reliability educator, educating our new hires.
He taught me a lot.
We are going to talk about the basics of non-abstract large system design, things that you need to know before you start designing. Then we are going to look at a problem statement, an exercise that you can use to hone your skills in non-abstract large system design. Then you can do some homework to actually try doing this, to actually try doing the non-abstract large system design. And finally, to not let you in the dark, we will give you an example solution of how we could actually design this large system.
And I'm going to talk about the basics. So in the basics, we're going to start with looking at requirements and how to scale. Then we're going to look a little bit at what to do in case of loss and failure, because failures are going to happen. We'll see how to keep state and how to handle data. And finally, we're going to put the non-abstract part in the design, the numbers. So let's start with the requirements. Before being able to develop any application, we have to look at what the requirements are. What do the users want from us? What is their use case? And when I think about requirements, I usually think about SLIs and SLOs as well. The service level indicators, or the SLIs, are some measurable aspects of the system that users care about. So availability, or latency, or data freshness are some examples. And then the SLO is the definition of what we want the performance of an SLI to be. So as an example, we can have an SLO that says the 99th percentile of queries is going to return a valid result within 100 milliseconds. Now, the users are not going to give the requirements in terms of SLOs. You're going to have to derive them. In our example, you'll get the SLO, so that's going to be easier. But in general, you'll have to figure them out. Tighter SLOs cost more money, but at the same time, the users might expect more performance that you can provide, for instance, due to historical reasons, because you've done better in the past. So what happens when you break an SLO? Because that's going to happen sometimes. We're going to violate it. That is when the SLA comes into place. So a service level agreement is the contract containing all the relevant SLOs and what to do in case we violate them. Externally, that usually means some loss of money. Internally, teams usually open an incident, and then they have to write a blameless postmortem of why it happened and what we can do to avoid it in the future. Now, when thinking about SLO, an important thing to keep in mind is future growth. How can the system scale to 10x? It should be possible to do that with minimal architectural changes. So I've talked about growth. Growth can mean planned growth, such as adding new features, or it can mean organic growth, users sending more traffic organically over time, or even inorganic, a large new user sending traffic that triples the amount of incoming requests. So how do we handle that? Our system has to be able to scale. One way to do it is via microservices, which are small binaries that provide one single function. Think only authorization or only storage. They do one single thing, and they do it well. So you can take your large monolithic binary and then split it into microservices. This is a very good place to speak a little bit about terminology. We usually make a distinction between a server and the machine. The server is the software. It is the running program that is serving requests, whereas the machine is the hardware part. It is a computer that runs one or more servers. So microservice A is going to run on a server, which runs on a hardware machine. So why do we want to use microservices? Microservices add a lot of flexibility. One single monolithic binary doing everything becomes really, really difficult to scale. I think you have one that does everything. It does authorization, authentication, routing, resource management, you name it. How do you know which part of it grows? How do you know which one to scale? With microservices, capacity planning becomes more of a reality other than an ideal state. So we can forecast how much we're going to grow in the future and plan accordingly. adding business logic is also very hard to do with a monolithic binary because it may often not be compatible with new frameworks or APIs. Whereas microservices are framework and language independent, so it makes it a lot easier to add new things to them. They can be written in different programming languages, and all they need is a remote procedure control mechanism to do message passing. Finally, microservices can have their own velocity. They can be released separately. They don't have to, but they can. So maybe one of the microservices here, microservice B, say, is a very critical one. So we want to be more careful when we release it. That does not mean that we have to slow down the microservice A and C release. Now JC is going to talk a little bit about failure and loss.
Yes, thank you, Julia, because failure will happen and loss will happen. There are many things that can fail in an application and in a machine. Just think about disks, for example. The longevity of an average disk is, let's say, about 3 years, which means that if you have 3 disks, one will fail on average every year. If your application needs, let's say, 90 disks, then there will be 30 disks failing every year. In other words, 2.5 disks will fail in any given month. There are many things that can fail. So for example, we have machines that can fail because their power supply goes out or because their network card goes out. Entire racks that house many, many machines can fail as well because of their top of rack switch fails or their power supply fails. Entire data centers can fail because there could be a hurricane coming over, or you could have a major utility power loss. If you have machines that are running the same binary, then you can have the problem that if the binary contains a critical bug, that all of these machines can no longer run this binary and the binary starts crashing everywhere. The worst case of failure is when you have a global configuration system. Just one little change in your configuration file and all your binaries could stop running if you have not protected against this. This is a very serious thing that you should pay a lot of attention to. Try to avoid global config systems that update all your binaries running at the same time. So how do we deal with failure? The easiest way, and I'm not trying to weasel my way out here, the easiest way is to make it someone else's problem. Let's go back to the disks for example. I said that disks will fail once every 3 years on average. What if you use a storage system that does replication, which means that you don't have to think about the disks failing? And not only you don't have to think about it, but any party that makes use of that storage system can assume that the disks will not fail because the storage system will actually take care of it. So make it someone else's problem. Many cloud providers provide services that if you use those, you make actually use of the safety that is built in them. Now, of course, you have to make sure that you can actually trust your cloud providers. Even cloud providers will not be up 100% of the time, so you will have to adjust for that. Be aware of limitations of services that you're using. You cannot trust on something being up 100% of the time, never, because everything will fail, even the service that you depend on. Think about how you can actually avoid being harmed by a service that you depend on not being there. Ways to defend yourself against failure are several. For example, avoid monolithic servers. Like Julia said, by decoupling the different functions in your big binary into small microservices, if one part of the service dies, then the other parts can still function. For example, it could be that your upload functionality goes away, but that your download facility is still there. You have to design handling failure in from the beginning. And try to spread risk. don't just rely on a single backend. Make sure that you have multiple backends that you can use and use them in a spread it out way. We call this sharding. Also, when you do get overload situations, then if you do things the naive way, things will fall over. Your first server will fall over because it gets too much load. That means that the other servers that are running will get even more load, and one after one, they will fail in a cascading failure. What you should do is build in degraded performance. What do I mean by that? Well, for example, if you normally serve 20 search results, then you could make only 10 search results available, meaning that you have to do less work. And the users will most probably not click as far as they would normally do. In other words, in the end, you have served less work and still the users are sort of happy. How do you achieve reliability? An important part is that because we know that parts will fail, we know that we need more of the parts. And at SRE, we like to think in N+2. What does N+2 mean? Well, it means that if you know that you need N parts of your service, for example, you need 5 machines, or you need 3 data centers, or you need to be in at least 7 racks, then you add 2 to that. Why 2? Well, one of them could be taken out for plant maintenance. And while the thing is down for plant maintenance, there could be some accident or whatever causing a other thing to go down as well. So if you have computed that you need 5 machines for a certain server, having 7 means that if a machine goes down because of its power supply, you can still have plant maintenance on another machine. That is why we use N+2. And now Julia is going to talk about how we keep state and data in our application.
Thank you. Why should we talk about this? Well, pretty much any application that accepts a user input and is expected to provide an output will have to store data, will have to have a mechanism to retrieve data, and will have to act on the data to manipulate it. All the interactions between the system and the data, it turns out, should be consistent, and they should follow certain rules. That is why we need to keep state. We need to have a global view of the data. Other reasons are performance and reliability. We don't want to duplicate work too much, for instance, for performance reasons, which is why we also have to keep state. Similarly, we may need to do leader election, hence reliability. However, it is very, very hard to do right. And so, if possible, we always prefer to do stateless. It is just easier. Now, regardless of the amount of data involved, it all comes down to global consensus. There is a reason why most cloud providers do not provide leader election services for consumers. That is because it is hard to use correctly. Global consistency, however, is very critical for large systems. We need it, for instance, for quickly discovering the data that is sharded in multiple locations. It is also important in order to find authoritative instances of other services, or, for instance, for the load balancer to find which workers to send data to. There are various already existing algorithmic implementations for this, such as Paxos or Raft. In distributed systems, when thinking about this, we usually think in terms of consistency, availability, and partition resilience. Now, we may want all 3 of them, but as a general rule of thumb, we can only have 2. As another rule of thumb, networks are not reliable. We saw that failure is going to happen, so we need partition resilience. And then we have to pick another one and handle the fact that we don't have the 3rd. Some existing systems do this by choosing availability and partition resilience and then going around consistency by doing eventual consistency. Google Spanner does that. So with Spanner, you can say how much stale data you are OK to read. If you can support older data, then the reads are really fast. However, in order to have consistent reads, it is going to be slower because you have to check with all the participants in the system. And this consistency also restricts how much QPS your system is going to be able to handle. So now that we've talked about data, let's talk some more. Data is not accessed at the same rate. Some data is accessed a lot more than others, and we have plenty of examples in the world about it. Media is one such example. So take Reddit, for instance. You're going to have a small subset of articles that are read by a lot of people. They have a lot of views, whereas other articles are only read a couple of times, maybe. Another example is YouTube, where you have a small subset of videos that are viewed billions of times, whereas others, again, have only a couple of visualizations. So why are we talking about it? Why is it a problem? It is a problem because if you access some data a lot, then your system may become overloaded. Or it may simply become slow, and users may notice it because of bottlenecks via I/O. So we have to find a solution to it, and one solution is sharding. You can shard your data into multiple locations, which makes hotspotting less of a problem. However, it also has downsides. You're going to need to have some sort of lookup server in order to find where that data has been sharded. And that lookup server adds some more time to the requests, but also adds an additional point of failure. Another solution is to add caches, which also help with hot data. So by doing this, you just move the data to a faster I/O to be able to handle it faster. If your data is on SSD, you can move it to RAM. If it is on HDD, you can move it to SSD. This improves user experience and reduces load on the backend. However, it is important to make the distinction between capacity caches and performance caches. Performance caches are there simply to make the access faster, whereas the capacity caches are used in order to be able to handle the entire load, and that is very dangerous because things will fail, as JC explained, and when they fail, if the capacity cache fails, then the system is not going to be able to handle the entire load by itself, and you're going to be in a bad shape. So if you do have capacity caches, they should not be included in your SLO because you're in danger of breaking it. Now JC is going to talk a little bit about non-abstract design, so he's going to put some numbers to those boxes.
Thank you, Julia. Yes, we are going to look at the non-abstract part of the design. And that means that you do the math. You have to think about with how many queries per second, QPS, will we need how many disks and how many machines. In the end, you will come up with a design where you will say, I will need this many machines and this much network capacity and this much storage. Note that for each of your components, you have to think about how much disk I/O am I going to do, how often am I going to access the disk, how much am I going to read from the disk and what the capacity is that I will need, how many queries per second am I getting from the outside world or from outside my service, sometimes also how many queries am I sending to other services. And of course, network bandwidth is very important as well. Now, when you do these calculations, you have to make things easy for yourself. And I'm not going to say that you should lie, but I will lie a little bit here. One day has 25 hours, because if you have to do the math about how many storage you will need every day, it is easier to calculate with 25 hours a day than with 24. And actually, it is only about orders of magnitude. So rounding up or down a little is totally fine. A month has 30 days, and a year has 300 days, or maybe 400, just depending on how easy it is for you to calculate. Also, when you do capacity planning, it is easier to use rounded off numbers. And when you do math using a calculator instead of back-of-the-envelope calculations, don't keep 7 digits of precision, because your input data isn't that precise to begin with. So now it is time to talk about our problem statement, the problem that you are going to try and design our system for. Let's see what we look at. We are going to design a photo system, a photo serving system that will initially be global for 1 million users, and we estimate, we don't know for sure, but we estimate that every user will be uploading a photo 50 times a day. The user interface provides two different types of pages. One of them is a thumbnail page, which shows 10 thumbnails of photos based on some search criterion, such as the user or a hashtag or things like that. And the other view that we have, the other UI view, is a detail of one single photo. A little bit about the sizes of these. We say that a photo is 4 megabytes in size and that a thumbnail is 256 or 1/4 of a megabyte in size. Note that these numbers are very specific and you can just take these as a given. There may be some other numbers where you have to make some estimates. Now let's talk about SLOs. The service level objectives that we want to offer our users. How well is our application behaving? Serving the thumbnail page with the 10 thumbnails should be done within 250 milliseconds for the 99.9th percentile. That means that 99.9% of these requests will return an HTTP 200 answer within 250 milliseconds. For the one image page, so one full resolution image, we expect 200 milliseconds within the 99.9th percentile. These SLOs are only valid for pictures that are from the past 30 days. So we don't have to think about pictures that are older than 30 days. We could extend our design for that later, but that is not important right now. So what can we use to build this? Our available infrastructure contains networking with an SLO of 99.99% availability. We have a storage system that has an SLA for latency of 100 milliseconds at the 95th percentile and a latency of 200 milliseconds at the 95th percentile for writing. The storage system is a bit strange. It is geared towards photo serving because if you store a large size photo, it will automatically thumbnail it for you, and when you retrieve data, you can retrieve either the photo or the thumbnails. This is globally replicated and eventually consistent within minutes. We will have multiple data centers in 3 regions in the world, in Europe, Asia, and North America. And these data centers may be down for 1 week every quarter for planned maintenance. Of course, they could also be down for unplanned maintenance or for accidents. The hardware that we have available for you is not the newest of the newest. We have 2 types of machines. Hard disk-based machines with 24 gigs of RAM, 8 cores, 10 gigabit Ethernet connection, and 2 2-terabyte hard disks. We also have SSD machines that have 24 gigs of RAM, 8 cores, and the same 10 gigabit network, but with 2 1-terabyte SSDs. You can use as many of these machines as you want, as long as you can explain why you need that many. Now for the homework. We would like you to make use of these services and note that the network and the storage will be SRE backed. Start designing a system for one single data center. Does it meet the SLO? What kind of hardware do you need to actually meet this SLO? Then expand this to use the 3 data centers that we have. How do you make it meet the SLO? And make sure that you run the numbers, so in the end you will come with a bill of materials. How many machines are you going to need? In other words, how much money is this going to cost? Remember the suggestion to use microservices. This will help you design the system.